Okay, so now we're going to look at hyperbolas, the last of the four conic sections. So I have two different hyperbolas on this page. One is vertical and one is horizontal. Each hyperbola has branches. So we have this branch here and this branch here. And the branches on a vertical hyperbola open up and down. They open vertically. And then on the horizontal hyperbola, the branches open left and right. They open horizontally. Inside each branch, we do have a focus. So it's very similar to a parabola in that case. Parabolas are these U-shaped things, and inside the U-shape we have a focus. Same thing with hyperbolas. However, please do not call a hyperbola two parabolas, because that is incorrect. The geometric shape of these is very different from a parabola, and then the properties are very different. So don't confuse the two. If you call these two parabolas, people will cringe when you do it. You don't want people to cringe. So hyperbolas have branches. Inside the branches, we have a focus. There's also asymptotes. Notice that each one of these hyperbolas has two asymptotes. The ends of each branch approach the asymptotes. So the asymptotes are going to help us draw our hyperbola. We also have vertices. Each one of these branches has a vertex. And then we have the center. And you can think of the center as the midpoint between the vertices, the midpoint between the foci, or the intersection of the asymptotes. So those are the parts of a hyperbola. And then down here at the bottom, we have the definition. A hyperbola is a set of all points such that the difference of the distances between any point on the hyperbola and two distinct fixed points, called the foci, is constant. And this definition hopefully looks very familiar to you because it is almost identical to that of the ellipse. The only difference is, obviously instead of the word ellipse, we have hyperbola, but the hyperbola has difference, or has sum, and a hyperbola says the difference. So the ellipse is the sum of the distances, and a hyperbola is the difference of the distances that are constant. So what that means is if I were to take some point on the ellipse or the hyperbola, and let's just look at the horizontal one. So if I look at this point right here, if I measure the distance to one focus and the distance to the other focus and subtract that, then that should equal the difference between this point, say, and I subtract the distances. So it's a little harder to see here than on the ellipse because we're talking differences instead of sums. But those, if I had my picture drawn accurately, that would be the what's happening, is those distances are constant. All right, so there's our definition there. I'm not going to derive this formula. It's something similar to what happens with the ellipse. You saw us derive that. You can do that for fun. You know, you're a little bored. You're stuck at home, shelter in place. What better to do? But what we're going to do is let's just look a little bit more at formulas and parts and all of that. So here we have a little more detail, not a whole lot more than what we had up there. So the formula for hyperbola, just center it at HK. So I'm just going to jump right there. We've been looking at our conic sections all throughout. So let's just look at HK. Take a look at these formulas. Look at the formulas. They're very similar, almost identical to the ellipse, except instead of a plus sign, it's a minus sign. And remember with the definitions, ellipse said sum and a hyperbola says difference. You can see that reflected into the formulas. The ellipse has a plus sign because we're talking the sum, and the hyperbola has a minus sign because we're talking differences. Now another big difference with hyperbolas, because of this minus sign, now order matters which way we subtract. So if your x term is positive, so the term that has the x, if that's the positive term, then your hyperbola is actually going to be a horizontal hyperbola. And then if your y term, the term that has the y in it, if that's the positive term, now it's going to be a vertical hyperbola. So that's one easy way to tell if you've got positive or negative, horizontal or vertical hyperbola. Another thing is this role of A and B. So the role of A and B actually tells you the slopes of the asymptotes. So the slopes of the asymptotes are plus or minus B over A. So you go up B units over A units, and one of them is always going to be a positive slope, one of them is always going to be a negative slope. That's why we have the plus or minus. And the other thing is that we have this thing called the transverse axis. So that's new. That's specific for hyperbolas. The transverse axis is the segment connecting the two vertices. So for a horizontal hyperbola, then the transverse axis is horizontal. And for a vertical hyperbola, the transverse axis will be vertical. So it's always going to connect the two vertices together. And the other thing that I didn't put on here, let's go ahead and add this on, is we have A, so we can see A and we can see B here. We'll see where they actually show up in the picture when I do my next example. But C is still the distance from the center to a focus. So there is a formula that relates A, B, and C, and this one, it doesn't matter which hyperbola you have, it's always going to be A squared plus B squared equals C squared. So there's an overview of the hyperbola. So now let's take a look at graphing a hyperbola, and we can see how all this stuff plays in. So the first thing is this hyperbola going to be horizontal or vertical? So think about that. See if you can remember what we said above. And we know it's going to be vertical because the y term is positive. So if the y term is positive, then it's going to be aligned along the y-axis. It's going to be a vertical hyperbola. We also know that the center, now be careful with the center. H is always with x and k is always with y. So h is -3, y, sorry, k is 1. So the center is going to be at -3, 1. And then we can see A and B. And again, A is always with x. It's always going to be the horizontal distance. And so A is 3, because A squared is 9. And then B squared is 16, so B will be 4. And then remember, we have this formula here, A squared plus B squared equals C squared. If A was 3 and B was 4, you might recognize this Pythagorean triple, but we can easily see that C is going to be 5. All right, so let's see. I think we have enough to start drawing this hyperbola. Let's see, I'm going to go ahead, I'm going to move this over here, make some room on the side. So let's draw this. I'm going to set up my axes. And the center is at -3, 1. So there's my center. Now from there I'm going to measure left, right, up, and down my A and my B. So remember A is 3, and that's always your left and right distance. So there's A right there. And then B, I go up and down from the center 4 units. And then this is a strategy that's commonly used. We're going to go ahead and draw a rectangle that goes through those points. I'm going to highlight those points, make them a little bigger so that we'll still be able to see them when I draw this rectangle. This rectangle is not actually part of the hyperbola. It's just going to help us draw it. So I'm going to draw that in with dotted lines. And so we have this rectangle. Notice I did not make those blue dots the corners of the rectangle. Those are just the midpoints of the sides of the rectangle. And the reason why I drew that rectangle is now I'm going to draw the diagonals of the rectangle, and that's going to end up being my asymptotes. And again, asymptotes aren't actually part of the hyperbola, so I am drawing those also with dashed lines. So now I have that. Now you don't have to draw the rectangle. I mean, you can go, we know that the slopes of the asymptotes are plus or minus b over a. So from the center, I go up 4 units over 3 units, and there's 1 point. And then again, I go up 4 over 3, there's another point. You can do it that way also, that will work. But a lot of people just make the rectangle. Do whatever you want to do, it doesn't matter. But now we're going to actually draw the hyperbola, and it's a vertical hyperbola, so that means the vertical points are my vertices. Sorry about my dog there, he's a little hungry. So I have my vertices there, and then I just draw the branches of the hyperbola. Remember that the hyperbola is approaching the asymptotes, so when you draw it, you do want to show those branches approaching. Don't do something like this. Don't do that, because wait, sure, it was approaching the asymptote, but now it's going away. Wait, that's not what's supposed to happen. That's not an asymptote. Remember the ends. It has to keep getting closer and closer and closer to the asymptote. Notice these 2 points right here. They're not a part of the hyperbola at all. They don't even get a name. They're just there. They helped us draw the rectangle. But these 2 points are the vertices, and then we know the foci are 5 units away from the center. So I can go 5 units from the center up, and there is one focus, and 5 units from the center down, and there is my other focus. Now I have my hyperbola. Let's go ahead and label everything, all the different parts. So the vertices, they're vertically aligned from the center, so we're going to be adding and subtracting from the y-coordinate. So remember the center was at -3, 1, but we're going to add and subtract b units. So that's the coordinates for the vertices. And we can go ahead and summarize that, or simplify them. 1 plus 4 is 5. And 1 minus 4 is -3. And if we double check, sure enough, at -3, 1, 2, 3, 4, 5, -3, 5, that was one vertex. And then -3, -3 is our other vertex. So there's our vertices right there. For the foci, same kind of thing. If we don't have a picture, but we know we're going up and down 5 units, then we can add and subtract 5 from the y-coordinate, which is going to give us 1 plus 5, which is 6, and 1 minus 5, which is -4. And again, we can see -3, 6 is the coordinates for one of the foci, and -3, -4 is the coordinates for the other focus. And then finally, we can say that the length of the transverse axis, in this case, because it was a vertical hyperbola, we're going to use the vertical distance b, and we're going to double it. So it's 8. And there we go. That's the hyperbola. So then the next video is just going to have a bunch of examples, and that'll be done.